Hey, thanks very much, Stu, and thanks to the Papers Committee for saying yes. I thought I would start with the preemptive apology. This really isn't a professional talk. I've spent a couple of months tinkering, and I'm not a neuroscientist, and I'm not a machine learning expert, so be warned. However, New Zealand does have an excellent array of environmental sensor data. And if we could have a chance to build something useful with that data, that would be really useful. In particular, would it be possible to know, we know when it's raining, and we've got historical data on how much rain it takes for particular rivers to flood. So can we get a machine learning model to learn from all of that sensor data automatically and give us a warning maybe a couple of hours in advance as to whether or not we need to evacuate? You know, that's something that seems kind of useful, and in particular, it might be useful to little councils who don't want to spend hundreds of thousands of dollars with consultancies if they could just run something out of the box to do something relatively useful. It doesn't need to get them all the way, but maybe they could get somewhere. And secondly, GeoNet is a fantastic resource. Who here has used GeoNet and submitted a felt report? Well, all of those, fewer people. So GeoNet does collect crowdsourced data on the human impact of earthquakes, and we can use that crowdsourced data potentially, or this is the hypothesis that I wanted to test with this project, we can use that data to predict the human impact a couple of hours before we get information from the field. So if we have a relatively severe, or if I feel shaking, can I just ask a computer to say, tell me if my family is likely to be hurt? Yeah. So what is this thing that I'm talking about? Well, it's a system for building artificial intelligences, and what's particularly unique about the system is that the people who produce it try to have very strong foundations in neuroscience. So this is the argument that they're going to make. Irrespective of what your brain is looking at or sensing or the domain that it's tackling, it's actually almost completely uniform in its physical structure. That means that the brain, or evolution, depending on which way you want to go there, has been able to create this system of general applicability that over time it can learn to model and represent problems of any problem domain. So let's actually have a go at implementing that hierarchical structure in software. Now, this is where I get a little messy in terms of, I'm just going to have to get a bit hand-wavy here. This is what I've sort of read up. The neocortex is hierarchical. If everyone, the neocortex is the part of the brain that is kind of the non-reptilian brain. I think it's the big bit at the top. It's actually, even though it's clumped up, it's actually about 2 millimeters thick all the way through. There are 5 cellular levels in a hierarchy, and there's a non-cellular level as well, from inputs to outputs. And through this sparse hierarchical kind of network, some magic kind of happens, and that's what we want to replicate in software. Now, what's interesting, I find, was this little quote that the same input data actually can be represented differently by the brain. If you were to utter the sentence, I ate 8 apples, the phenomes, what your ears are telling your brain is exactly the same, but your brain is actually able to pick up 2 sentences of exactly the same input data. And so there's also a temporal link, which comes in really useful with a term that I'll introduce later called temporal spooling. No, temporal pooling. Okay, so some motivations. This seems really cool, right? Like, it's actually, if we can do this right, and if the promises that they're making are correct, this system should be able to learn itself onto any problem. Like, just it can apply AI. So this is actually kind of one of the things that kind of piqued my interest was that, let's go through the whole quote, there is a trade-off between how much memory is allocated to each level of the model and how many levels are needed. So it's building up an internal representation of its input data. And fortunately, HTMs, which stands for hierarchical temporal memories, it's a term of art used in this project, automatically learn the best possible representations at each level given the statistics of the input and the amount of resources allocated. Now that seems pretty spooky, being able to actually get the machine to represent its input data as, the best, that's a strong claim, the best possible representation. Here's another one from this white paper that they released in 2011. Just going into this, reinforcing that the brain is very uniform and yet it's able to be useful in very many areas. The system is self-adjusting. NuPIC is designed to deal with input streams. So it doesn't care if it's computer vision, natural language, radar data or flight traffic control data or temperature gauges. And my personal view is that over time, more and more of these sensor streams are going to become available as more processes are implemented in software. As soon as something is automated with software, it becomes extremely easy to become an instrument and to just begin to move forward. Now, the last thing which I found really compelling was that this company, Numenta, which hosts the project, in about June, I believe, just open sourced it. So they have a commercial product which does a lot of these tools, and they decided, hey, the very core of that is this implementation of these learning algorithms, and we're going to release that to the community. And I thought, well, one way to externally validate for them and say that it's a useful thing to do is, in about June, I saw this post on Reddit, I think, and I thought by the time September comes along, I will have given that a go as a way of saying thank you to Numenta for being really brave. So we're introducing some terminology here. I'm going to say, I'm just putting this slide up just to say that once you start digging into the details, there is a barrier to entry. And in particular, you need to start to become slightly familiar with both the specific application of their own language, as well as some of the scientific terminology as well. They do start talking about neurons and dendrites and things. But the one I'm kind of keen to talk about is sparse distributed representations. So this is typically how things are done inside NuPIC. It'll take your data, which is typically encoded in Python as just a dictionary, and it will split it into these very long arrays that are very sparse and almost exclusively zeros. And if you look at this array here, I've tried to highlight in black where there are matching ones between these two input streams. You can see, so the idea is that where there are matching ones, there is some similarity between the input data. And so the process that NuPIC is attempting to do is to sort of abstract away whatever it is that you're giving it into one of these representations and then kind of see if what now exists as a bit array matches what it has previously seen. And because if it knows that you are mostly there, if you have a number of matching ones, the two patterns are semantically similar. Now, if I was to, so how does this actually work? We'll talk about the way the encoding process is later, but possibly to give some slightly clearer intuition about what might happen, say you have an encoder for integers. And even though there are an infinite number of integers, say in your problem domain, you only care about the values between 0 and 100. There might be a percentage value or something. Well, you can split up the space arbitrarily into 100 buckets. And values that are, say, between 10 and 12 will have ones that are roughly sort of 10% into this array space. But there will be an overlap. Now, I don't know if that got all the way to explaining exactly how these work, but hopefully that got somewhere to explaining what the system is trying to do. It is trying to encode information in a very sparse way and then match it with information that it's already received and patterns that it already knows. Just to enable people to sort of, the example code in the repository is this thing called hotgym. And it's temperature data from a bunch of I believe it's sort of Australian gyms. And the gyms want to know, like, when do I need to turn on the fans? Because I don't want to use a lot of power. So if I can get my fans to turn on just before it gets too hot for my customers, I'm going to save money and actually provide a better service to my customers. So that's kind of the business value that they're trying to provide. And this is code this is what the input data looks like that you receive if you check out the repository. It's a CSV file with there are three lines of metadata. The heading are your field names, like most CSV files have a heading line. Then there are two other ones. We tell NuPIC what data types to use. And then we've got these kind of flags. Now, S stands for, it means sequence ID, but I think one way to think of it might be primary key if you come from a database background. And T is a flag telling it to treat it like time. I don't know why you need to tell it that it's time twice, but apparently that's the way the system works, and so we'll kind of go along with the grain on that one. So just to kind of reaffirm people's intuitions here, that column means that's the name of the gym. Here we have where the gym is. That's the time in which the sensor was taken. And this last value is consumption, or I think it's energy use. But we can think of it as some sort of arbitrary value that we want to predict in the future. So the business value that we want to know when this consumption value changes. And we're asking NuPIC to do that. And this is actually all you need to do to get going. You'll notice that they're not using what we would consider sort of Pythonic conventions for variable naming and so forth. The project is largely C++, and they have their own kind of, they kind of tweak PEP 8, let's say. So the first thing we do is input this, we build a model. And I'm going to explain what these model parameters are. Effectively, it's a dictionary with a whole bunch of options, like a configuration file that's been parsed. That's one way of thinking of it. We tell NuPIC that I want you to predict that consumption field, that was the one on the far right that you saw in the previous slide, suck in the data, and feed in, for each line in the data, give the model a new reading. So what we're simulating here is, even though we have a CSV file, we're simulating receiving information from a data stream periodically. Just to make in case you're not sort of super familiar with Python, what's going on in these 4 lines is that we create a dictionary based on the CSV file, and then we modify a couple of the values. What we're doing here is converting the consumption value from a string to a float, and then we're going to create a datetime object from the string representation in the CSV file. Okay, and then we feed it into model.run, and then we, quote, get our result. Okay, so, and apparently that is it. Like, it seems once you've you get a prediction for every single piece of information you provide it. You will always get a predicted value, and in fact, you can ask for a predicted value for, say, in the next 5 steps. So if I was to provide 5, please, NuPIC, tell me what you expect the consumption value to be in 5 in 5 updates. These are 15-minute segments, so please tell me what you think it's going to be, this consumption value will be in an hour and a half. I'm just going to go with this result value first, because the input data is a little messy. So what you see on the left is NuPIC's expected value for consumption after what it predicts will happen right next. And on the right-hand side is the p-value for that. So you can see that 5.28, NuPIC expects that is roughly 69% likely. So what we've created is a probability distribution of what will happen next. You might think, one of the things that you could do if you're building this system is say, well, if none of those values occur, or nothing within that probability distribution occurs, you know that some anomaly has happened. So you can also use this for detecting errors. And in fact, that's one of the commercial applications for this Numenta product called Grok. Now, after 5 steps, NuPIC thinks, with a relatively high degree of certainty, that this consumption value will increase. So with all of those values, so they're sorted by their probability likelihood. So they're actually sorted by their values rather than their keys. But this is kind of what you get out. And you're also given this convenience attribute of the dictionary called multi-step best predictions. So that's what you receive as output from the model. It's a bit of a black box. You don't know how it's kind of generated it. You don't actually get access to that long bit array, as far as I can tell from what I've experimented off when I've been playing around. But this here is the input. Just down to flagging, there are a lot of knobs that you can tune. And one of the things that I had a lot of hassles with, is that, like, where do I kind of begin? To ask it the right questions, and which of these do I choose? And so I want to distill this. This is just a dictionary. That's that model params value that was right in the top. So there are 4 main sections for that model parameters thing. One is these sensor parameters. So we're telling NuPIC a little bit about what data I'm actually providing it. SP stands for spatial pooling. That means we have that long bit array. It will attempt to pull things together to make things that are semantically similar be represented in similar ways. Temporal pooling will try to bucket time. So if you're providing updates, say, every second, but what you care about is getting predictions for, say, minutes in the future, it can do that bucketing for you. And CL is called the cortical. It's the parameters for the cortical learning part, and it's sort of not super useful, so that was down. Oh, I've gone the wrong way. I want to just talk about SP params, because this is where we talk about encodings and how we generate these bit arrays. For that CSV file, this is what you get. You need to give NuPIC an idea of the field name in the CSV file that you're talking about. So we have 4 encoders here, and one of those CSV values is actually being represented in 3 ways. The person who's designed this model has said, if we just look at those timestamp ones, that I think as an operator or a gym, that it will be useful to know if it's a weekend or not, because I know that my usage data for my business changes on the weekend. Likewise, the time of day kind of matters. There's more likely to be more use during the day than at night. And additionally, day of the week can be thought. So there are these weird numbers, 21.1, that look really odd. I just want to get to this. There are a number of classes that have been generated to interpret the types of data that you are likely to send it. This adaptive scalar encoder. Does anyone remember when I said that you might be interested in your business problem between the values of 0 and 100? Well, say that's fine. Well, what if you don't know the span of integers that your model was likely to receive or your sensor data is likely to give you? Well, this one will actually change the window in that fixed bit space for you. The date encoder will take a whole bunch of your date time values and then create these submodels. It's kind of fun to look at in the code, but one of the things to note is that we have these two values provided by NuPIC. One is what they call a windowing function, like a window value and a radius. Sorry to kind of bore people with the details, but I know there's going to be some small proportion of the audience who's really interested. I just know that it took me a lot of time to figure out how this works. I really want to share people so you don't have to go through the same hassles. The window and the radius will try to tell NuPIC how to split up the space. So if we're talking about the day, if we want to know if it's weekend, we want to know that you might want to split up that bit array to, say, like 2 space. You might have on or off, like effectively a binary space. However, with the defaults provided by the example code, they split all the times up into 21. So each day is split into 21 hours effectively, and each week is split into 21 days. The 1 means is the radius, which is how much overlap between 2 bit arrays matters, as far as I understand it. Yeah, so there's actually like a lot of, it isn't quite living up to the promise of being able to be like a self-describing, self-learning system. However, you're given this tool, which they released sort of, I think about 10 days ago, which is a genetic algorithm implementation for searching through the search space about exactly which parameters and how to encode them and everything else. But it has another dictionary which you can describe. So I just thought it'd be worthwhile to quickly run through that. We provide these info values, which I think are related to logging. The source data, it's a really strange URL there. That actually relates to an environment variable NuPIC, which you're kind of forced to define, which refers to the root directory of the project. So that was kind of a trick for new players. We again need to tell the system which values we actually care about. And then we talk about bucketing of time. And so we can tune lots of knobs and say, well, actually, I care about days, or now I also say, well, what are the kinds of values that I want to predict? And this multi-step inference is, I would like you, dear NuPIC, please tell me what will happen in several steps' time. And I would like you to tell me, in this case, 1 step in the future, and I would like you to talk about the consumption variable. -1 for iteration means just go until you kind of converge at a value that is useful, but if anyone that's familiar with genetic algorithms, it can just go on and on and on. Swarm size means it's effectively the number of how thorough it will be in finding the correct parameters. You can either set that as small, medium, or large. So now talking about my data. GeoNet provides an amazing API. It's comprehensive. There's several 100,000 earthquakes. It provides all the felt reports that have ever been submitted, and their modified Macaulay values as well. So we go back to our original question, and can we? Unfortunately, I'm not sure. It's really quite. It's been much harder to work with data sets that are non-trivial than I would have expected. In terms of the training, just takes a lot of time. And the other problem that I faced was I would like, if anyone's familiar with the modified Macaulay scale, I guess you could think of it as, it's like Richter scale, but for damage. So 1, I believe, is, didn't feel it, and by about 6, things are falling off the wall. And I didn't want to know, if I was to, say, make a qualitative statement about how hard people are feeling this earthquake, I don't just want a scalar value, like an integer or a float. What I wanted is a distribution of how much people, how many ones, how many modified Macaulay 3s, how many modified Macaulay 4s, and so forth. And this predicted field only provides me with the option of one output. So talking about the CliFlow database, this is really cool stuff. NIWA puts up a whole bunch of infrastructure to give people access to all of the rain data that it has, and there's a collaboration between them and the Met service and so forth. So it's very comprehensive. It's sort of open. You need to ask for permission, but they will give you it. However, and in fact, the data that is accessible to you as a sort of a public user is pretty real time. So if I think it's within an hour, you'll be told what the weather is doing in Kaitaia, for example. Unfortunately, so can we predict the likelihood of severe weather events based on these input streams? Again, I think so, but I have not been able to verify it over the course of the last couple of months. Unfortunately, I found it much harder than I anticipated to actually get the historic data for say, rivers. I wanted to know, the question that I was asking originally was, will it flood? And do we need to evacuate? Well, I can't tell NuPIC when it will flood if I don't know. So I have access to the rain data, but that's not really enough to do anything useful. And I was pretty unsure after rereading the license for CliFlow that I'm not actually allowed to distribute publicly any results from data produced. So what I was intending to do is ask for help and say, if anyone would like to collaborate tackling these two problems, we can just share the code, but not share the data, I think would be a kind of interesting proposition. And if you're willing to kind of put in the effort to learn what the terms mean, you'll probably get there. And especially if you have a machine learning background, you'll probably pick it up really simply. There are actually there are many more tools that I'm talking about in the code base to actually enable you to make applications. And Numenta has only been in the open source business for, since June, but they are doing a great job at fostering community. They've, already talked at OzCon, and they have a really supportive mailing list, and they're extremely responsive. So if you want to help me try to figure this out, there are some contact details. Otherwise, that's the end of the talk. Thanks.